Hi guys, and welcome to Learn Extra Maths Literacy Session 10. In this session we are going to introduce probability to you. Now I'm sure a lot of you have heard of probability, but you're not quite sure what it's used for other than working out your chances of winning the lotto. But in reality, probability has a lot of applications and is used widely in the fields of science and engineering. So let's discuss probability in greater detail. A probability is really just a likelihood or a chance of an event or something happening. And we measure this on a scale from 0 to 1, which I will get into a little bit detail in a little while. First, let's just go over what an event is. Now, you will see this phrase often being used when we deal with probability. An event is just a collection of one or more outcomes of an experiment. So it's really just looking at all the outcomes of an experiment and listing down these outcomes as events. Now, if we are absolutely certain that an event will take place, then the probability is 1. And if it's absolutely impossible that something will happen, then the probability is 0. And that brings us to the probability scale. Let's just show you what a probability scale is. Now remember, I said that probabilities are measured on a scale from 0 to 1. So if I represent this on an actual number line type scale, with 0 being the start, and then the probability of 1 being an absolute certainty, and then somewhere in between, which we'll say is about halfway, 50%, that's giving you a 50-50 chance of something happening. So 0, it's where it's an impossible event. So that's absolutely impossible that something's going to happen. And here I'm talking about something like getting a 7 on a dice. Now you know it's not possible to get a 7 on a dice because your dice only has up to number 6. So it's impossible that that will happen. And then a certain event is something like the sun rising every day. We know it's definitely going to rise in the east, so it's definitely a certain event. That probability would be 1 or 100% if we think of it in percentage terms. And a 50% probability or 0.5 probability means there's an even or a fair chance, or a 50-50 chance that something's going to happen. And here, if you think about, if you toss a coin, your probability is you can either get a heads or a tails. So that's a 50-50 chance that you could get a heads, or a 50-50 chance that you could get a tail. All right, and this is generally, everything falls in between here. As I said, all the different possibilities falls in between 0 and 1 on your probability scale. Probabilities, as I was mentioning during showing you the scale, probabilities can be expressed as percentages. They can also be expressed as fractions. And these can all be used interchangeably. So I can talk of a probability as a fraction, percentage, or a ratio. The probability of any event happening is the number of ways of that event E happening, all divided by the total number of possible outcomes. So if you take the number of ways that something can happen divided by the total possible outcomes, that will give you the probability of that event happening. So guys, what we'll do is let's use this in application, working out our probability. This is example 1, and this is an application of finding the probability of an event E. So we are told that a fair die is thrown, and then they ask us what is the probability of getting a 6. A fair die is just a fair dice. So you have a dice, you throw it, what is the probability of getting a 6? Now remember, in order to work out the probability of any event, it's going to be the number of ways that that event can happen all over the number of possible outcomes. All right, so the first thing we're going to do before we determine the probability of getting a 6 is we are going to list all possible outcomes. So when you throw a dice, what are all the different numbers you could get from the dice? So what are all the possible outcomes? Now you know there are 6 sides to a dice, each of them having a certain number of colored dots. So if you throw a dice, you basically could get any of those numbers coming up. You don't really know what number is going to come up. So all the possible outcomes, you could get a 1, a 2, 3, 4, 5, or 6. So that's basically any side or any face of that dice can be shown. You're not sure which one is going to come up. You can't tell for a fact, and that's why it's called a chance or a probability. So those are all the different possible outcomes. Now, the only successful outcome, or the one we are interested in, is getting a 6. So the only way we can get a 6 really is if we throw a 6. So there's only one way in which that can happen. And there are 6 possible outcomes that could happen. All right, so we've got 6 numbers that could come up. The only time we will be successful in this experiment is when we get a 6 on this dice. So if I would like to work out the probability of getting a 6, and this is how we express probabilities, I'm going to say the probability of getting a 6 on the dice is going to be equal to the number of ways that we can get a 6, which is just one way, divided by the total number of possible outcomes, which is 6. So therefore, the probability of getting 6 on a die is equal to 1/6. Or you could represent this as a percentage, as I said to you before. Okay, the next part says, what is the probability of not getting a 6? So once again, let's work it out in exactly the same way. We know that the probability of getting a 6 is 1/6. So what is the probability that some other number is going to come up? So you throw your dice, you really want a 6, but what is the probability that you're going to get some other number? So 2, 3, 5, anything else besides 6. So we do it exactly the same way. We list all our possible outcomes, and because we've just worked it out, I'm not going to do it again, but we've just shown that the possible outcomes are 6. There are 6 different things that could come up, the 1, the 2, the 3, 4, 5, or 6. And we are looking at the probability of not getting a 6. So the number of ways of not getting a 6, of not 6, well, that would happen if we got a 1, because 1 is not 6, obviously, or if we get a 2, or a 3, or a 4, or a 5. So in other words, not getting a 6 means getting all the other numbers on the dice. And the number of ways that can happen, 1, 2, 3, 4, 5 ways in which we cannot get 6 on the dice. So therefore, the probability of not getting a 6 is going to be the number of ways in which we cannot get a 6, which is 5, all over the total number of possible outcomes, which is 6. Therefore, the probability of not getting a 6 is equal to 5/6. Now, what we call this probability, the probability of not getting something, we call that a complement. So, if I want to work out the probability of not getting a 6, which is the complement of getting a 6, what I could have done is I could have said the probability of not getting a 6 will be equal to 1 minus the probability of getting a 6. And we know that the probability of getting a 6 we worked out was 1/6. So the complement of that would be 1 minus 1/6, which is, once again, 5/6. And as I said, you can leave that as a fraction. So this was just a different way. This is in thinking of this question in terms of complements. So we can leave the answer in a fraction, or we can change it to decimal form. All right, let's do part C. Now we want to know what is the probability of throwing this dice and getting 4 or more. So first, let's list all the possible ways, or the number of ways, possible ways of getting 4 or more. So that would happen, we want to get 4 or more than 4. That would happen if we got a 4 on the dice. So if you throw the dice, you get a 4, then you're successful. Or if you get a 5, because 5 is more than 4. or if we get a 6. So there are 3 different ways we can get more than 4 on a dice. So the number of possible ways of getting more than 4, or 4 or more, is 3 ways. Okay, so that would happen if we got a 4, a 5, or a 6. We know that the total possible outcomes, since we're dealing with a dice, is equal to 6. Therefore, so this was the number of possible ways of getting 4 or more. Now this was the number of total outcomes, which is 6. Therefore, the probability of getting 4 or more will be equal to the number of ways of getting that, which is 3, divided by the total outcomes, or the total possible numbers that you could throw in this dice, which is 6. And 3 over 6 we know is a half, or we can say that's 50%, or we can leave it as a fraction, whatever you prefer. But generally, we can refer to probabilities as fractions, percentages, or ratios, as I said to you in the beginning. Okay, guys, so we've just looked at a basic example of how we can work out the probability of an event occurring. Let's move on to example 2. Here we are told that a factory checks 90 soccer balls and finds that 30 have a fault. Okay, so we are dealing with a possible 90 soccer balls, and of that 30, special something happens to these 30, they have a fault. All right? If a ball is chosen at random, and that's very important in probability, you will always see this chosen at random. In other words, it's not a biased experiment, so you don't actively go out and seek those, or you puncture them or whatever. It's completely random. You just go in and pull out whatever the first thing is that you see. So it's completely random. It cannot be biased in any way, any of your experiments. What is the probability that it has a fault? All right, so we know that 30 balls out of the 90 balls have a fault. So the number of possible outcomes, so if you just go into this whole lot of soccer balls and you pull any one out, you could pull out any one of the 90 balls. So the number of possible outcomes, you can pull out any one of the 90. There are 90 different balls that you could pull or take out. And the probability of finding one with a fault, so we know the number of possible faults. So the number of balls with a possible fault is equal to 30. There are 30 balls with a fault. So therefore, the probability of getting a ball with a fault out of these 90 balls, well, there are 30 that have a fault. There are 90 balls altogether. So therefore, 30 divided by 90 will give us a third, or you can write that as approximately 33.3%. if we were to write it in percentage form. Okay, so the probability of getting a ball with a fault out of these 90 is 33%. Now the second part says we want what is the probability of getting a ball that does not have a fault. Now there's more than one way to do this. We can think of it as a complementary event, which means it is just 1 minus. So the one way to do it is to say 1 minus the probability of the ball having a fault, which is what we've just worked out in the one previous. Or we can do it by saying, well, the number of balls that don't have a fault, the number of balls, soccer balls, without a fault, well, if 30 have a fault, then it means that since there are 90 balls, 30 have a fault, 90 minus 30 is 60. So therefore 60 balls do not have a fault. So that's the number of ones that you could pick from that don't have a fault. So the number of balls without a fault is 60. We know we are choosing from a pack of 90 balls. Therefore the probability of not getting a fault or of no faults in the soccer ball is going to be equal to the number of balls without a fault, which is 60, divided by the total possible number of balls, which is 90. And 60 divided by 90, we can write that as, if we simplify that into 2/3, or it's roughly 66.7%. All right, now if you had done this by working out 1 minus the probability of the ball having a fault, it would have been 1 minus a third, which is 2/3, which will give us exactly the same answer. Okay, so you could have done this working out, as I said, with the complementary, or doing it from scratch and working out, subtracting the number of balls with a fault from the total amount of balls, and then seeing that there were 60 without a fault. Okay, now the next thing we're going to move on to is example 3. This one's a little bit different from what we've done so far, and it requires a little bit more thought. Let's move on to example 3. We are told that in a school with 20 educators, 8 own cars and 5 wear glasses. Okay, with probability questions, it's very important to take note of every little bit of information you are given, because every little thing will come into play later on. So we've got 20 educators or 20 teachers in total. 8 of them own cars and 5 wear glasses. 4 of the teachers who own cars, remember 8 of them own cars, so 4 of the teachers who own cars also wear glasses. Calculate the probability that if you picked a teacher at random, the teacher will, and then they've asked us a whole lot of questions on that. So let's look at the probability, or let's work out the probability of a teacher owning a car, which is part A. We know that there are 20 teachers that we are choosing from, and 8 of them own cars. So therefore, the probability of any teacher owning a car is going to be equal to the number of teachers with a car, which is 8, divided by the total number of teachers in the school, which is 20. And then we can simplify that to 4/10. Which is equal to 40%. So therefore, there are 40% of all teachers in the school own a car. Now for the next part, for part B, they've asked us to calculate the probability of the teacher chosen not wearing glasses and owning a car. Now, this is quite a simple example. You might be able to sit there and over time figure the answer out, but I find that a much easier way to work out a question like this is to draw up a table. So let's draw up a table with the information that we've been given. And the most important thing in this table is our headings and deciding where everything should go. So what we're going to do is, we know that we've divided the school up into teachers with a car and without a car, and then teachers who wear glasses, and then teachers who don't wear glasses. So in one of the rows I'm going to write, we're going to look at the teachers who own cars, and then one of the other row can be the teachers who don't own cars, so they don't have cars, no cars. So we basically divide this table up into little bite-sized pieces that will help us to put down the information we've been given. We've also been told something about teachers wearing glasses, and then teachers with no glasses. Okay, in these type of what they call two-way tables, or later on in the next section on probability, we'll be looking at contingency tables. That's when we'll get into greater detail. But this is just a little version, a baby version of the tables you're going to use later on. So we label each of the columns and each of the rows according to the information they've given us. We know that this group of educators are broken up into wearing glasses, not wearing glasses, owning cars and not owning cars. And then we just have tallies at the end, so totals at the end of the column and the row. We know that the total number of teachers owning cars is 8, so we can put that down. And we know that the total amount of teachers in the school altogether are 20. So if there are 20 people in the school, 20 educators in the school, if 8 of them own cars, then it makes sense 20 minus 8 is 12. Therefore, there are 12 teachers without cars. So that's just by a process of reasoning that we can work that out. We are told that 5 of the teachers, so in total 5, wear glasses. And therefore, if there are 20 educators in the school, and 5 wear glasses, it's very easy to work out how many don't wear glasses. We say 20 minus 5 and we get 15. We are also told that 5 of the educators wear glasses. Okay, so we've put that in, and we've told that there are 4 teachers who wear glasses and own cars. So now that we've worked out what each of the totals are at the ends, we need to now fill in the middle part of the table. So we need to fill in the body of the table. We are told that 4 teachers wear glasses and own cars. So in the row where we've got wear glasses and own cars, in that one we can put down 4. That's the condition that both of these satisfy. So if 5 teachers wear glasses altogether and 4 of them own cars, that means one of those 5 does not own a car. So again, once again, by process of reasoning. Then going across, we can see if 8 teachers own cars, 4 of them wear glasses, it makes sense that 4 will not wear glasses. 8 minus 4 is 4. And then lastly, we know that the teachers with no cars are equivalent to 12. So if one of those wears glasses, then 11 of them, 12 minus 1 is 11, 11 of these teachers don't have a car, and they also don't need glasses. So from this table, we can write down the probability of selecting a teacher who does not wear glasses and owns a car as 4 over the total number of teachers that you are selecting from, which is 20. 4 over 20 we can simplify to 1 over 5, which is equivalent to 20%. So therefore, the chance that you will select an educator from the school who wears glasses and owns a car is 20%. So guys, we've just looked at a few examples on how you can work out some basic probabilities, and now we're going to move on to something called Venn diagrams. Venn diagrams are another useful way to list all the possible events that are happening. We call the set of all possible events a sample space. Okay, so when we list all the possible events into one little diagram, we call that a sample space. Now, a Venn diagram, as I will show you in a little while, it shows a sample space and all the possible events, as I've just said. Before we go into that directly, first let's just discuss mutually exclusive events. Now, these are events that cannot and will not and do not happen at the same time. So, for example, if you toss a coin, you can either get a head or a tail. It's not possible to get a head and a tail. So, therefore, the probability of getting a head or a tail is a mutually exclusive event. So, these are events that do not happen at the same time. So, these don't happen or not happen at the same time. They will not happen at the same time. So suppose there are 2 events, A and B, where the outcomes of A are the numbers 1, 2, and 3, and then the outcomes of B are 4, 5, and 6. Now, we can actually represent all of this on a Venn diagram, and I'll show you what a Venn diagram looks like. It is literally just 2 little circles that we use to represent all of this information. So let's get our circles up. All right, and in each of these circles, we put down all possible events from A and all possible events from B. We then close this off, and we call this entire little box the sample space. All right, so in this diagram, this little box, the black box, we call that the sample space. That's called S for sample space, which shows all possible events. When there are no elements in common between them, as I said to you, these are called mutually exclusive events, and this is also known as disjoint, but we are just really interested in the word mutually exclusive for your purposes. And in each of these circles, what I'm going to represent are the two sets of mutually exclusive events. So the one circle is going to represent all of the possible outcomes of set A, and then the other circle represents all the possible outcomes from set B. So in these little circles, I put down in A, I can have the numbers 1, 2, or 3. And then in set B, we have the numbers 4, 5, and 6. All right, so this entire set, as I said to you, that's called your sample space, which lists down all of the events. Set A has the numbers 1, 2, 3. And then set B has the numbers 4, 5, 6. They have no numbers in common, and therefore they are called mutually exclusive. So what you really need to remember for your purposes is that mutually exclusive events do not have any events or any outcomes in common. The next very important thing that we will look at is called union and intersection of sets, and I'm going to explain this to you once again using the Venn diagrams. So first we have our sample space, and in this sample space we are going to list two sets, A and B. So to list your sets, we always use our little circles. And in this case, I'm going to let the circles intersect each other. All right, so we've got two circles, and each of these represents a set A and a set B. So say we have just any two sets that I take, the union of the events A and B is an event that will consist of all the outcomes that we will list. So say I had the numbers in A, I had 1, 5, 3, and then 6. And then the set B had the numbers 2, 3, 4, and 6. So A has the numbers 1, 5, well, let's list them in order, 1, 3, 5, and 6. And then B has the numbers 2, 3, 4, and 6. Now, as you can see, they have certain numbers in common. Now, the point where these numbers are in common, that's we call the intersection of the two sets. So that's called your intersection. And both of these sets combined together is called the union. So the intersection, once again, consists of the outcomes that are common to both sets, and the union is an event consisting of all outcomes of A and B. The way we represent the union of two sets, A union B, we use this symbol, the U that you used to and see in everyday life. We just don't put a little stroke at the end. So we say A union B, and in that set we will list all possible outcomes. So where all of these overlappings happen, and this would be the set 1, 2, 3, 4, 5, and 6. So basically for A union B, what we've done is we've added together set A with set B, and we've listed all the possible outcomes. So I've got 1, 2, 3, 4, 5, 6. Those are any possible outcomes that you could get from combining those two sets together. The intersection we represent with an upside down U. So we say A intersection B, and that is really where these two sets have numbers in common. And if we go to the diagram, to the Venn diagram, we can see that the only two common numbers are 3 and 6. So these are the shared numbers. So A intersection B is 3 and 6. All right, so let's go through that. Again, we looked at the union and the intersection of these two sets A and B. We saw that the union of the two sets was where we added both sets together and listed all possible outcomes. So it was literally taking set A, adding it to set B with no repeat outcomes. So even though there's a 3 in both of them, I don't write the 3 down twice. I just want together, what will all the possible outcomes be? Together it would be 1, 2, 3, 4, 5, 6. We don't repeat repeated elements. And then the intersection will be the shared numbers. So what do these two sets have in common? And the shared numbers here are 3 and 6. Guys, we're now going to look at an example using Venn diagrams that I've just shown you. This is example 4. We are told that in an all-girls school, it held a sports clinic during the holidays, and the sports offered were tennis, hockey, and swimming. Girls could participate in as many of the sports as they liked, and the diagram illustrates the participation with each circle representing a sport. So firstly, let's go through the diagram and let's interpret what the diagram is saying to us. Remember, where the two circles intersect each other, or where the Venn diagrams intersect each other, that's where we have the intersection of two of the sports. So the different sports here, we have tennis, hockey, and swimming. And we see that in this one, we've got an intersection of 25 girls between tennis and hockey, and then an intersection of all 3 sports, so 10 girls doing tennis, hockey, and swimming. And then this little part here, the 15, tells us there's an intersection between swimming and hockey, so 15 girls swim and play hockey, and then 20 girls swim and play tennis. Okay, so those little overlaps, remember, they represents the intersection of each of the sports. This number, the 40 by itself there, that tells you how many girls play hockey. So 40 girls play hockey. And then this number 35 tells you how many girls swim, and there are 35 girls that swim. All right, let's look at the questions that they have asked us. Firstly, we would like to know how many girls participated in all 3 sports. So there, what you are looking for in all 3 sports, we are looking for an intersection between all 3 sports. All right, so I'm just going to highlight the intersection of all 3 sports, which is that point 10. So we can see that 10 of the girls participated in all 3 sports. Okay, and that's directly from your Venn diagram. We then want to know how many girls played only hockey. So if we go back to the diagram, remember, these overlappings show the points where they played hockey and other sports. And this number 40 by itself, that's the point which shows the number of girls who played hockey alone. So 40 is the number of girls that only participated in hockey. Okay, so that does not form part of your intersection, which is where they play hockey and other sports. We are now going to look at an intersection. We want to know how many girls play tennis and swim. So let's go back. So we're looking for where tennis intersects swimming, and we see that that's the point 20. So there are 20 girls who swim and play tennis. Therefore, that is our intersection. Right? So the number of girls that play tennis and swim, there are going to be 20 of them. And then we want to know how many girls only swim. So here we're not looking for intersections. We're looking for girls who are only swimming. So therefore, they're not, for example, playing hockey and swimming, which is 15 girls. They only swim, and that's that point there, which is 35. So therefore, there are 35 girls who just swim. And then finally, they say, if 175 girls attended the sports clinic, how many played only tennis? So what they are asking you for here is this is what's missing. We need to know, what is that? How many girls played tennis only? So we know 40 girls played hockey only, 35 girls swam, and we want to know how many girls just played tennis, so we're not interested in any of these intersections. They have told us that 175 girls attended the clinic. So if we want to work out how many only played tennis, we've got to say 175 minus the other girls who participated in hockey, swimming, and then we have to minus the intersections as well, but we've got to be careful here not to double count. So I would say 175 minus 40, which is the number of girls that played hockey, plus we're going to add to that, it's got to be 170 minus, and in this bracket I'm going to add all the intersections that hockey made with tennis and swimming. So therefore that's going to be 25 girls who played tennis and hockey. Then there were 10 girls who did all three sports. And then we had 15 playing hockey and swimming. From there, we've got a minus the number of girls who swam and played tennis, which was 20. And then we've got a minus the number of girls that just swam, which is 35. So if we take away from 175 all of these, and you see that we don't overcount, so we don't take into account an intersection twice, you will get an answer of 30. So therefore, we can fill this in now. There are 30 girls that just played tennis. Alright guys, so that was an example on Venn diagrams. Venn diagrams are not very common, but some schools do include them in exams and tests, so make sure you understand what your Venn diagram is saying to you. Okay guys, let's move on to example 5, which is once again dealing with probability. There are 6 chocolate flavored, 4 strawberry flavored, and 5 vanilla flavored ice creams in a box. What is the probability that an ice cream chosen at random is chocolate flavored? Now, if we want to work out the probability of getting a chocolate flavored ice cream, we've got to first realize that if there are 6 chocolate, 4 strawberry, and 5 vanilla, when you put your hands into the box, there are going to be 15 different choices for you, because there are 15 ice creams altogether in the box. So the 15 I got by saying 6 chocolate plus 4 strawberry plus 5 vanilla. So you add that all together and that gives you 15 ice creams that are in the box. We know that of those 15, only 6 are chocolate flavored. So the probability of pulling out a chocolate flavored ice cream is going to be the number of chocolate flavored ice creams, which is 6, over the total number of ice creams, which is 15. Now you can leave this as 6 over 15, or you can use your calculator and work out what that is in percentage terms. 6 divided by 15, and then we've got to times it by 100, will give us 40%. So you have a 40% chance of reaching into this box and pulling out a chocolate flavored ice cream. Next, we are asked, what is the probability of not getting a chocolate flavored? Now, as I said to you before, when you're working out complementary events, you can simply say 1 minus the probability of getting a chocolate flavored ice cream, which in this case is going to be 1 minus the 40% that we just worked out there, which in decimal form is 0,4, and we'll get 0,6, which is 60%. Or if you don't like to do it that way, we can look at what the possible outcomes are. If we don't want a chocolate flavor, that means that we are just restricting ourselves to 4 strawberry and 5 vanilla. So the successful ways to get to something that is not chocolate flavored would be 4 plus 5, which is 9. In that way, you'll be getting your strawberries and your vanilla flavored. So therefore, 4 plus 5, that's the number of favorable ways, or the possible ways that we can get something that's not chocolate. All right, and we know altogether there are 15 15 ice creams in the box, so therefore the probability of getting something that's not chocolate would be the possible ways you could do that, which is 9, over the total number of ice creams in the box, which is 15. And 9 over 15 would simplify to 3 goes into 9 3 times, and 3 goes into 15 5 times, which once again will give you an answer of 60%, 0,6 or 60%. We're now going to look at the last example on this probability section. This is example 6. We are asked, what is the probability of rolling a dice and getting an even number less than 6? So what is the probability of rolling a dice? Now remember, when you roll a dice, there are 6 possible outcomes. You can get the numbers 1, 2, 3, 4, 5, 6. And we are interested in getting an even number less than 6. So we know the total outcomes, the number of total outcomes is 6. And the favorable outcomes, the one that we are interested in, the number of ways that you can get an even number less than 6. Remember, even means it's a multiple of 2. And they're just going to be, the numbers to choose from here are really just 2 and 4. Because if you think about your dice, it's got numbers 1, 2, 3, 4, 5, 6. The only even numbers that are less than 6 are 2 and 4. So therefore, the favorable outcomes is just going to be 2. All right? So the probability of getting an even number less than 6, I'm just going to write less than 6, is going to be the 2 ways that that can happen over all possible outcomes, and there's 6 possible outcomes, and 2 over 6 is a third, which is equal to roughly 33.3%. All right, let's move on to part B. We want to know, what is the probability of not getting an even number less than 6? So the number of ways, or the number of possible things that you can get, which will not be even numbers less than 6, let's just list that down. You can get the number 1, since that is obviously not an even number less than 6. We could get the number 3, also not even, 5, which is also not even. And then 6 itself, because obviously 6 is not less than 6, 6 is equal to 6. So there are 4 different ways that you can get an even number less than 6. Therefore, we can write down the probability of not getting an even number less than 6. And here are possibilities where all the numbers that were not even and that were less than 6 were 1, 3, 5, and 6 itself, because 6 is equal to 6. So therefore, the probability of not getting an even number less than 6 is going to be all our possibilities, which were 4, over the total probable outcomes, which is 6. And therefore, 4 over 6 we can simplify to 2/3, which we can write as 66.67%. Now, the other way you could do it is, maybe some of you realize that this probability of not getting an even number less than 6 is actually the complementary event of what we just worked out in the first part, which was we worked out to get the probability of getting an even number less than 6. We worked out that that probability was a third. Therefore, if we would like to work out the probability of not getting an even number less than 6, we could say that probability of not getting even numbers less than 6 would be equal to 1 minus the probability we worked out in the previous part of this question, which was 1 minus a third. That will give us 2/3, which once again will give us 66.67%, or 66.7%. Exercise 1. 11 cards are cut out, and each one has a letter of the word mathematics as shown below. If a card is chosen at random, calculate each of the following probabilities. A, the probability of getting the letter A. Part B, the probability of not getting the letter A. C, the probability of getting a vowel. D, the probability of getting a consonant. And E, the probability of getting the letter M or the letter T. And F, the probability of getting a vowel or a consonant. And then finally G, the probability of getting a C or a vowel. Okay guys, so now you've had a chance to look at the exercise. Let's go through it. Exercise 1, you are told that 11 cards are cut out and each one has a letter of the word mathematics, which is how come there's 11 cards, because obviously there are 11 letters in the word mathematics. They say if a card is chosen at random, calculate the probability of getting the letter A. So in order to work out the probability of getting the letter A, all we do is we go to our 11 cards and see how many cards have the letter A on them, and we see that there are 1 and 2. All right, therefore the probability of getting the letter A out of a possible 11 cards is going to be 2 out of 11. The probability of not getting the letter A, now the one way you can do it is 1 minus the probability of getting the letter A, which would be 1 minus 2 over 11. which is equal to 9 over 11. Or you can go back to the pack of cards and you can count all the cards that don't have the letter A, and once again you'll come up with the number 9. There are 9 cards with other letters other than A on them. Therefore, the probability of not getting an A just by counting would once again be 9 over 11. We are then asked to find the probability of getting a vowel. Remember, your vowels are the letters A, E, I, O, and U. So therefore, we have to go to the set of cards and look for all the vowels. And we see that we have the letter A, so that's 1. The letter E, that's 2. The letter A again, that's 3. And then the letter I. So therefore, there are 4 vowels in the set of cards that spell out mathematics. So therefore, the probability of getting a vowel would be 4 out of 11. We then want the probability of getting a consonant. Now, a consonant is all of the other letters that don't include your vowels. So the one way you could do it is you could say 1 minus the probability of getting a vowel. Alternatively, you can go to your set of cards and then count all the other letters that are there. So that would be 1, 2, 3, 4, 5, 6, 7 cards that are not vowels and that are consonants. So that would be 7 out of 11, the probability of getting a consonant. We then need the probability of getting an M or a T. All right, so these are mutually exclusive events. You can either get an M or a T. You're not going to get both. Therefore, this would be equal to the probability of getting an M plus the probability of getting a T. And if we go to our pack of cards and count the number of M's and the number of T's, we see that there are 2 M's and then 1 and 2 T's. So each of the probabilities individually, the probability of an M is 2 out of 11, and the probability of a T is also 2 out of 11. Therefore, the probability of getting M or T is 2 over 11 plus 2 over 11, which is 4 over 11. We then want to find the probability of getting a vowel or a consonant. Now, we've already worked out that the probability of getting a consonant was 7 out of 11, and the probability of getting a vowel was 4 out of 11. Therefore, the probability of getting each of these are going to be the probabilities added together. Remember, these are mutually exclusive. A letter can either be a vowel or a consonant. It can't be both. Therefore, it will be the probability of getting a vowel plus the probability of getting a consonant. And we're just going to add them together. So it's going to be 4 over 11 plus 7 over 11, which is 11 out of 11, which makes perfect sense. The probability of getting a vowel or a consonant basically means what's the probability of getting a letter, any letter. And obviously, because these are only letters, it's going to be 100% probability that you're going to choose some sort of letter from a pack of letters. All right. Or some sort of alphabets. Then the last part would like us to work out the probability of getting a C or a vowel. So that's going to be the probability of C plus the probability of getting a vowel. So we have to first go and see what is the probability of getting a C. We already know what the probability is of getting a vowel. We see that there's only one card with the letter C. So therefore, the probability of getting a C would just be 1 over 11. We've already worked out the probability of getting a vowel is 4 out of 11. And therefore, the probability of getting a C or a vowel would be 5 over 11. Exercise 2. In a class of 25 learners, there are 15 girls. 7 learners wear glasses. 3 female learners wear glasses. Calculate the probability that if you pick a learner at random, the learner will be male. And part B, the learner will be male and not wear glasses. Here we are told that a class of 25 learners are being looked at, and there are 15 girls. And obviously if there are 15 girls, straight away you can tell something. You're looking at 25 learners, 15 are girls, so therefore straight away you can say, well, 10 must be boys. So the class can be easily divided into girls and boys. 7 learners wear glasses. Once again, an easy deduction from that is if 7 people wear glasses, we're looking at 25 altogether. That must mean 18 don't wear glasses. We are told that 3 female learners wear glasses, and we are asked to calculate the probability that if you pick a learner at random, the learner will be male. Now that one is quite straightforward because we know that if there are 15 girls, there have to be 10 boys. So therefore the probability of getting a male learner will be the number of boys, or the number of males, over the total number of students, which is 25 or learners, And if you would like, you can simplify that into a percentage form. So 10 over 25, we can write that as a percentage, as 40%. So therefore 40% of this class is male. Now for the next part, they would like us to work out how many learners are male and they don't wear glasses. Now it's going to be much easier for this example to draw up a two-way table. So what we're going to do is we're going to divide the class up into the number of female learners and then the number of male learners. And then we can also divide it into the learners who wear glasses and the ones who don't wear glasses. Remember, in these tables, once you've decided what goes into the body of your table, the end rows and columns need to contain your totals. So I've got a total for the rows and then a total for the columns. All right, we know that altogether there were 15 girls, so I can put that total in straight away. And we know that there are 10 boys, and altogether there were 25 learners. We are also told that we are told that seven people wear glasses, so we can work out how many people don't wear glasses. 25 minus 7, which is 18. We are told also that of the girls, 7 learners wear glasses and 3 female learners wear glasses. So if we look just at the girls, 3 of them wear glasses. So 3 of the 15 girls wear glasses. So therefore 12 of them must not wear glasses. If altogether 7 learners wear glasses, 3 of them are female, then 4 of them have to be male. If there are 10 boys in total and 4 wear glasses, 10 minus 4 is 6. That means that 6 boys must not wear glasses. And obviously you've got to make sure that all of these columns and all of these rows add up. If they don't add up, you've made a mistake. Okay, so if we go across, they add up. If we come down, they add up. They've got to add up in going across and going vertically as well. All right, so let's answer the question. What is the probability of choosing a learner that is male and not wearing glasses? So really what we're looking for is the intersection of the row and column. So they're male and they're not wearing glasses. So I'm going to go to the male section, and I see that's here in this row, and I'm going to look where that intersects with not wearing glasses. And we see that that intersects there. So therefore, there are 6 boys who don't wear glasses. So the probability that you select someone that is a boy and that doesn't wear glasses is going to be 6 out of, you've got 25 people to choose from, so it's going to be 6 out of 25, which as a percentage would be about 24, well, it would be exactly 24%. All right, guys, so now we've come to the end of this introduction on probability. The best way to learn probability is to practice. It is a section that requires quite a lot of work, so make sure you understand exactly how to work out all of the different probabilities. You need to work out the probability of getting a number, the probability of not getting something, and you need to work out the probability of mutually exclusive events. So you need to be able to work all of those out, and all that's going to require from you is a little bit of practice.